Number 2 asks you to first identify the population, the sample, the parameter, and the statistic. So as a reminder, the sample is the group from which you actually collect your data. So in this instance, it would be the 36 students from your SRS. And then the statistic is just some value describing your sample. So I know that I collected data from 36 people, and I found that 17 of them avoided school lunch. So that would be my sample proportion if I take 17 out of the 36. So the sample proportion who avoids school lunch is equal to p hat, the 17 out of 36, or you could say about 47%. We would like, ideally, for that to describe our population. Now, the population is the group from which the sample is drawn. So if I only surveyed 36 students, I only represent students. So I want to have my population be all students at the high school. And then the parameter is just the same thing I was describing earlier with the proportion of people who avoid school lunch, but it's for the whole population. So this is the true proportion of students who avoid eating lunch at school. I'm not sure, did I erase the at? Avoid eating school lunch, never mind. So this is just P, not P hat. So then part B says, it turns out that the population proportion is 0.32. What shape would the sample distribution of p hat have? Justify your answer. So remember, we had a test for looking for the shape for our sampling distribution of sample proportions, and it's your large count condition. Did I have that already? Or didn't? No, I did. So I'm checking my large counts condition. So for this problem, it would be checking my sample size n times my population parameter, which is just told to me a second ago to be 0.32. So I'm just going to take my sample size, 36, I'm going to multiply it by 0.32, and I'm getting 11.52. Your large counts condition says n times p should be at least 10, and so should n times the complement of p. So I'll take 36 times 0.68. So I'm still going to be getting something that's at least 10. So because I've passed my large counts condition, we now have evidence that the sampling distribution of my sample proportion is approximately normal. That's the only test you have for the sample distribution of p hat. If, though, I wanted to look at my sample distribution of x bar, that's part C. The researcher also calculated the average number of times that a student ate at school in a week for the sample of 36 students. What shape would the sample distribution of x bar have? Now, I don't know the shape of the population. It is unknown. It was never mentioned to me. But it technically doesn't matter because you have a large enough sample size. The central limit theorem lets you say, hey, who cares what the population shape is, as long as your sample size is at least 30. So the central limit theorem applies since the sample size is large. Since n equals 36, which is at least 30, the sampling distribution of x bar is approximately normal. So it would not have mattered if it was extremely skewed left. The fact that I took a large enough sample, my distribution of averages of those samples will still be normal. Then part D says about the 10% condition. Now this applies to both of these sampling distribution, the one for p hat and the one for x bar. So is the 10% condition met, and why is this condition important for a statistician to consider? So the 10% condition is making sure that your sample size is essentially small enough. And because my sample size is presumably less than 10% of all high school students, because it's said to be a large high school, I essentially can ignore the lack of independence that's going on for this problem. The simple random sample was not selected with replacement, so technically I don't have independence. Technically I shouldn't calculate my standard deviation. But if your sample size is small enough, it rounds to about the same thing so that you can go ahead and calculate correctly an approximate standard deviation. Then it says, if the researchers went back and collected a bigger sample, so now 90 students, What would this do to both unbiased estimators, the distribution of p-hats and the distribution of x-bars? Remember, this is that inverse relationship. When you do a bigger sample size, it decreases your variability. So both would have their variabilities reduced so that estimates become more precise. So they're not nearly as spread out and variable. It would just get shrunken in and be a lot more consistent. And then if the researcher wishes to reduce the standard deviation of the sample mean to half the original value, what sample size should they use? So I'm talking about the standard deviation of sample means. So I'm just going to write out, I'm talking about my sigma sub x bar. And I want it to be half of the old standard deviation. So half of the old sigma sub x bar, half of the old answer to sigma over root n. But the question is, what does it do to the sample size? So I need to look at what will be under my square root. I need to also write in that my old sample size was 36. So that's going to be changing when I incorporate this 1/2. So I'm going to ignore my numerator, by the way. It's some population standard deviation that I'm never going to ask here. But if I want to put both of these items under a square root, the inverse of square rooting is squaring. So the square root of 4 is the same thing as a 2. But if I have it written as a square root of 4, then I can go ahead and multiply it with my square root of 36. If I want half of the original standard deviation, the inverse relationship tells me it needs to be 4 times its original size, sample size. So now instead of having a 36 in my radical for my sample size, we found that the new sample size would be 100.